Welcome to Mathematics with Tom. I am Tom, excuse me. And today we're going to take a look at circular and harmonic motion. And to do this, I'd like to return to our spring. Remember our spring? Let's see, we come up a little bit. We had a spring that we suspended from a ceiling. And this time we're going to do the same spring problem, but this time we're going to put it maybe on the floor. So I'm going to make a little spring here. This is where my spring attaches to the ground. And let's do this. Let's give it 2, 3, 4, 5, maybe 6. We'll go 6 of these coils up. Okay. So this is my spring unloaded. That's just my spring, no weight, and at rest. Now, the next picture, we're going to do the same thing that we did from the spring hanging, and that is we're going to put a mass on it. So when we put this mass on the spring, the mass is going to bring me to right about here at rest. So let's draw this. Now I have the same number of coils here, so just to make our picture make sense, that would mean I'd have there. There should be 2 more in between there. 1. And probably 2. And this time though, let's put our mass in here. So there's my mass. Let's see. Make it a little smaller. There we go. Center it. You make it a little this way. This way. There we go. That looks pretty good. So there's my mass. Here, I'm going to call it some mass M. And notice that what happened is when we put the mass on the spring is compressed. Okay. Now, step 3 will feel very similar to what we just did. So in step 3, what we're going to do is we're going to reach down, grab my spring, and I'm going to stretch it back up to its full length. So we're just using our force to lift the mass into its starting position. So now where we're going to be is we're going to have our mass here. Make it a little bigger maybe. Not much. Okay, so here's our mass M. And this time the spring is going to be stretched all the way back up to its extended position. There we go. Now is where the fun begins, and that is what we're going to do is just let go of the spring. We're going to let go of our spring. That's going to be picture number 4. Well, in the same way that it went up, you can see my grid too, it would also go back down too. So it's at 4, the very bottom here, at 4, my bottom picture looks like this. So now my spring is compressed into this space here. So it's all tightly wound up at the bottom. Well, it reaches the bottom. It still has the same mass. It reaches the bottom, and then what does it do? It goes right back up to the top. So now I have this process that from picture 3, it goes down to picture 4. And then it gets to the bottom of picture 4, and it goes right back up to picture number 3. And if I was just to stand there and watching this, all I would see is the ball going down, and then it would go back up. And then it would go back down, and then it would go back up. And you would just see it going over and over, up and down in a straight line. Now, here's what else we learned. And we need this as well. This was described by the second order differential equation, m for the mass of the object, y double prime for acceleration, plus k is the spring constant according to Hooke's law, times y equals 0. Well, we went and we solved this problem. We solved this problem by saying, all right, well, our null solution is probably something of the form of e to the st. Well, we solved that, and we said that S is plus or minus I times the square root of k divided by m. Well, then we said that writing the square root of k over m it's just a lot of extra writing. It's kind of cumbersome because most of the time what we do is we don't solve m at y double prime plus ky. Most of the time what we do is we solve y prime plus, equals, we solve y prime plus k over m. Y equals 0. And that should be a double prime. But instead of writing k over m, it's accepted that the square root of k over m is called omega. And so we solve the differential equation y double prime plus omega squared times y equals 0. Now, notice that we have what we have. So if S is plus or minus I omega, should be equals plus or minus I omega. Well, this says that my solutions, my null solutions, which are the only solutions since this is the null equation, is y of t is equal to e to the plus or minus I omega t. And it's at this point that I want to try to show you how the exponential function represents the motion that we see. So in order to do that, I'm going to come up to my screen here. Make judicious use of my space. Okay, and then let's put a circle around here. I know that really is cheating using that circle function, but man, do those look good. So there's my circle. Now remember that if I have e to the I omega t, well, that is just some point on this unit circle. Right there. This would be the point of some e I omega t. That's all that is. Well, if you recall that e, this is the same as the cosine of omega t plus I sine of omega t. And the beauty of a complex number is that it takes two parts to represent one number. And let me show you how this is, what this is telling us. If I was to try, and we'll say that, what if we try y of 0, and y again is e to the I omega t. Well, this is just e to the 0, but that's just 1. But that's not a complex number. Well, it's not if you write it like that. It is if you remember that this is really the cosine of 0, that's 1, plus I times the sine of 0. Well, that's I times 0. There's the complex number, so at t equals 0, I am at this point right there. Now let's try another point. How about a simple one, like just to get an intuition? Y of pi over 2. Well, that is the cosine of pi over 2. That's just 0. Plus I times the sine of pi over 2. Well, that is 1. That's the complex number of 0 plus 1i. That would be represented at this point. And the idea here then is that e to the I omega t, as t increases, represents a circular motion. It's a continuous motion around the unit circle or a circle of radius r. Well, that's what E is trying to tell us. It's trying to tell us that this motion happens over and over and over. So if you think of an electric motor or a gas-powered motor, they have harmonic balancers that keep it from wobbling. And that's exactly what it does. You can just track the circle. Now, what we're going to do is, this is circular motion. This is circular motion. So now, when circular motion, is projected with respect to time, this is called harmonic motion. Harmonic motion. Now, you might say, how in the world, or what in the world does that mean? Let's take a look. And the answer is actually in the bottom left-hand corner if we look at our spring. So I'm going to put my resting place. Let's make this our ground zero, if you will. Okay, there's my baseline. I'm going to give it a vertical axis as well. Okay. Now, you could make this height of anything. If you want to change it, just multiply it. But notice that it goes up to 1 and then it goes down to 1. Or we could just say it goes up to some value a and goes down to some value minus a. But for simplicity, let's just look at the value of 1. Well, what does it do? Notice that we started up. This was our start right here. So I'm going to put a point there. And then we let the spring go. And when we let the spring go, it passes down, and eventually notice that it passes right through here, through this zero level, and it continues right back down to the same level at some other point in time. Well, then what does it do? Then it goes right back up, and it has to pass through this middle point, but then it goes right back up to where it's completely extended out. And then what does it do? It just keeps on going. It keeps on going forever and ever. Well, if we measure this time in radians, like pi, well, then what have we done? We've tracked a circle. Now, notice at the very top, when you let go, it's going to be it's starting at 0. So it has to build up some speed. It's going to build up its speed, and then it's going to go faster, 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 faster. But then it's going to hit a fastest point, but then it's going to start slowing down. Why? Because now the spring is compressing up against it, and it's going to bottom out. But then it's going to change all that direction. It's going to start pushing, pushing, pushing. It's going to really get to where it pushes hard, and then the spring isn't pushing as hard, so it's going to slow down gravity, and the spring will run out, and it's going to come back down. Well, look at what that would do. That would look like this. It's going to start slow. It's going to get faster, 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 and then it's going to start to slow. And it's going to come up, it's going to start slow, and then it's going to get faster and faster, and then it's going to start to slow. And then it's going to do it all over again. So we could put this in lots of different forms of time, but look at what I've done. This is 2 pi over omega. And this next 0 point, this next intersection is 3 pi divided by 2 over omega. And then this next value here is going to be pi over omega. And then we sign this value as pi over 2 over omega. Well, what have I just drawn? When I map this with respect to time, notice that what we get is we get the cosine of omega t curve. That's what it is. So circular motion is projected into harmonic motion, which is represented by 2 parts. Cosine, well, that's the one that we just looked at, but according to our original exponential answer, sine is also a possibility. How is that? There's a few different ways. You could look at a shift of cosine to line up with sine. Or another way you might use sine would be this. Let's come back. Let's grab another color for a moment. how it's, let's just use our same curve, but a different color. What if I was to be so crazy here as to maybe put like a little firecracker here. This is a firecracker, and it's burning. And when that firecracker goes off, what's going to happen? Well, it's going to be starting right here. And then it's going to be pushed up to the top of the spring. So it's going to explode off of there. Then the spring and gravity are going to start. The spring will lose energy. Gravity will pull, and it's going to stop. But then the same thing happens. The firecracker is done. So it started with a zero initial condition for its position, but we gave it some instantaneous boost. But then what does it do? Well, then it comes back down. And it comes back down, and it keeps on going down. It goes down fast, and then it slows down. Then it comes back up. Well, what have we just seen? What is this? This is the sine of omega t. And that is how circular motion and harmonic motion are related and what our equation is trying to describe. I hope that helps, and thanks for watching.